Hello everyone and welcome back to lecture 6. In this part of the lecture we are going to talk about transient heating and cooling. As chemical engineers we mostly deal with steady state systems. We like to have everything in flow, and in steady state it means that the temperature of the system is not changing in time. But there are some situations, for example, when we are starting a plant before it reaches a steady state, the temperature of the system has to develop over time. Okay, and that phase of the system is called transient heating or cooling, depending on if you're doing heating or cooling. But also in a lot of other applications, for example in pharmaceutical or in niche chemical applications, we use another kind of reactor that is called a batch reactor. It means that we don't have continuous inlet and outlet flow from the system, but we just make the system or cook the system in a batch. Okay, and we want to know that when we start heating, how long it will take for the desired temperature to achieve. Okay, and this phase of change in temperature over time is what we call transient heating or cooling process. Okay, so this is very important in chemical engineering in many different applications. So here, for example, I'm showing you a chemical reactor. Okay, and here this is a batch reactor, and here you can see that you have the stirrer inside this system, and outside of this reactor you have the jacket where you have a lot of these coils, and inside this jacket you have, for example, steam as a heating fluid, and the steam is providing heat to the fluid that is inside this batch reactor. Okay, so let me show you a simple video here just to give you an idea what is happening inside this reactor. So let me pause the volume. So here you can see that this is the inside of the reactor, and the stirrer is mixing the fluid because we want to achieve a constant temperature. Okay, and the jacket of the reactor, that is the outside jacket, has some steam connection that is actually heating the fluid that is inside this reactor. Okay, so I think they will show the jacket here. So you can see that it has a jacket here, and you can see this pipe here that is measuring the fluid, the heating fluid that is providing heat to the bulk of this fluid that is being mixed. Okay, so these kind of reactors are very common in pharmaceutical or fine chemical applications. Okay, so this is what we saw in the previous slide. So you have the inner reactor. Okay, and this reactor has some fluid in it that is with a mass m. It means that it has a constant volume. That liquid or the system inside this reactor has a constant specific heat capacity, and then it has a certain temperature, the starting temperature of the process. And then you have the outer fluid, that is the jacket around the reactor, that is supplying the amount of heat Q dot. And the fluid inside this reactor, most likely it's normally steam, and it's at temperature TF, so that's a constant temperature. And it has the surface area, the jacket has a surface area of A, and because the heat is being transferred across a surface, so we have the overall heat transfer coefficient, that is U. Okay, and we have the equation for heat transfer that we will use in this situation, that is the heat transfer across a surface. So we have Q dot should be equal to UA, that is the overall heat transfer coefficient. It means that how effective the heat is, times the surface area of the jacket or the area of heating, and times the driving force, that is the temperature difference available in the system, that is the temperature of the hot fluid minus the temperature of the fluid that we are trying to heat. Okay, so the maximum driving force. So before we go into further detail of this transient heating and cooling analysis, we want to answer a few questions. Okay, so the first question is that if this mixing system or this batch system is at a constant temperature, or is the temperature changing in time? Okay, if it is at a constant temperature, it means that you have already achieved your desired temperature and there is no further heating required, and it means that your system is already achieved steady state. But if the temperature is changing in time, it means that you are in a transient state. Okay. So because we are looking at transient systems, so it means that the temperature is a function of time. It means that temperature is changing in time. Okay. And now we have further two more questions. Question one is that if the temperature is changing, what is the rate of this change? Okay, how quickly the temperature is going to change. And second thing is that is related to question one is how long it will take for the temperature to change. Okay, so how long it will take the temperature to reach from a temperature of T to a temperature TF, that is the heat temperature of the heating fluid. Okay, yeah. So we have to obviously answer these questions, and to answer these questions, we have to make some assumptions. So first assumption that we make is that the temperature throughout the system is constant. Okay, so it means that because of the mixing inside the vessel, the temperature of the whole bulk of the fluid is constant. And if that is true, it means that we can look at a section of this batch reactor over an interval of time delta t. Okay, so this analysis can give us how the temperature or the energy within the system is changing. Okay, so to do that, we look at the energy balance for the whole system over time t. So if you look at this equation, so we know that when we start the reactor, there was some liquid inside, and that liquid, because it was at a certain temperature, at a certain fixed temperature, we had some energy content. At time t that is equal to 0, it means that we are at the starting point of the system. And then we started to heat up the system by inputting energy from the hot fluid through the jacket to the cold fluid, that is the bulk of the liquid, over a time of delta t. Okay, and if you add these two, we get how much energy, what is the increment in energy over a time interval of t plus delta t. Okay, so how the energy has changed. So if you look at the governing equations, so we know that when we are talking about heating a fluid, and if the fluid is not, for example, flowing, if you are just, let's say, if you are heating up a pan of a fluid, so we can write the energy that you are inputting in that system is equal to the mass of the system, the mass of the liquid times its specific heat, how quickly the liquid is going to change its temperature, times at what temperature you are heating. Okay, and this temperature in this case is a function of time because it's going to change over time. So that is the energy that is within the system when we start. Okay, so that is this second part of the equation. Let me put the pen here. So this is what we have, and then we have the energy, that Q dot that we use in the previous equation from here. From here, so we know how much energy we are actually providing through the jacket over an interval of delta t. So that is the change in energy that we are providing through the heater. Okay, through the jacket. So the sum of these two gives us how the energy of the system is changing. It means that how the temperature change in a time interval of t plus delta t. Okay, so if you rearrange this equation, we can write it as in the form of Q dot. So we have mCp T at time t plus delta t minus temperature at initial time divided by the time interval itself. Okay, so we can further simplify this equation and write it in this form. Okay, and you will see why we did that in the next slide. So if you look at this equation here, okay, let me go to the next slide. Yeah, if you look at this equation here, you can see that if delta t approaches 0, this becomes the definition of differential. Okay, it means that how the time is changing over delta t. Okay, so that is the definition of differential. It means that the differential of temperature over time. So we can write this part as delta t over dt. Okay, that is the time and that is the temperature. And if we know that this equation here gives us how the temperature of the system is changing if we are giving heat that is Q dot. But here in this case, we are just looking at a system that is not flowing. So that is the how the energy of the system is changing from temperature T to a temperature TF, for example. While in this case, what this equation is providing is the heat transfer across a surface. Okay, so this is the internal heat of the system, while this is the heat that is coming through the heat exchanger. Okay, so it means that this heat is coming from the surface, from the heating fluid to the fluid, the bulk of the fluid. Okay, but the total amount of heat, whatever is provided by the heating fluid, actually is going to go in the bulk of the fluid that we need to heat. So we can compare these two equations, and we get the equation here that these two equations are equal, because the rate of heat transfer should be equal in those two situations, because there is no accumulation of heat. And we can further simplify this equation in the form of differential. Okay, so we can write dt over, we can take the temperature here on this side, and we can make this side the time equation, the delta t. Okay, and now we can apply the boundary conditions to further simplify this equation. Okay, so we know that when the time is 0, it means that we are at the starting point. The temperature T is equal to the initial temperature, so that is T naught. While when we are at an arbitrary time T, it means that any time T, the temperature is an arbitrary value of the temperature. It means that depending on how the time, the lowercase t is changing, the temperature is changing according to this time variable. So if we apply that boundary condition to this differential equation, so here we have the temperature T is going from T naught, that is the starting point, to any arbitrary value of temperature at time T. And on the right hand side, we are integrating from time, because it's starting from 0 to an arbitrary value of time, that is T. Okay. So if you solve this integral, and so if you do the integration of this variable, we get log T minus T. So Tf is the temperature of the fluid, and T is any temperature at time T. And then we have on the right hand side, we have UA MC MCP, and the integral of delta T from 0 to T is actually just T. Okay, so that is very simple integration here. And then we can rearrange this equation slightly further by applying the limit. And if you apply the limit here, we get this equation. Okay, so we have a fraction of temperatures. Okay. So if we keep working on this equation, we can further simplify it. So now we can write it in the form of, we take anti-log on both sides. Okay, so if you take anti-log on both sides, the log from the left hand side of the equation will cancel out, and you will have fraction temperature, that's what it is called. So that is Tf minus T at a certain time, divided by Tf, that is the temperature of the fluid, minus the initial temperature of the fluid, and that is equal to exponent raised to the power UA over MCP T. Okay, so that is the time function. And we can further simplify this equation by replacing this part of the equation. So we rearrange it slightly further, and we replace it with a variable what we called time constant. Okay, and the reason we call it time constant, because if you look at it, it means that once you know what kind of system you are using, this variable is constant. So you know how much quantity of fluid you have in the system. You know what the fluid is, because the Cp of the fluid depends on the fluid itself. You know what kind of heat exchanger you have in the system, because U is constant here. And A, you also know what is the surface area of your reactor going to be. Okay, so by fixing these parameters, you can calculate what is tau, and if you have a fixed geometry and a fixed fluid, this tau will become constant. Okay, We can rewrite this equation in now this simplified form. So this temperature fraction is equal to e raised to the power minus time over tau. And if you look at both sides of this equation, we have two dimensionless equations. Okay. Sorry. So t is in time and tau also is in time. So if you, after this lecture, please try to put the values of these different parameters in this equation and see what is the unit of tau. It should be second. And if you do that, you will see that this part of the equation, the right hand side of the equation is dimensionless, while on the left hand side you can see that this is temperature difference divided by temperature difference. So again, the unit is there is no unit, so both sides of the equation is not unitless, and it means that this is a dimensionless equation. Okay, so now this temperature fraction, if you look what this equation is showing you, that if you increase the time to infinity, it means that you give it very long for the heating fluid to heat the bulk of the fluid, the batch fluid. After a time of t is equal to infinity, your temperature, this t that is a function of time, will reach Tf. Okay, it means that after infinite time, this whole fraction will become 0. Okay, so it starts from t is equal to 1 when the time is 0, but when you give infinite time, this temperature will become Tf as well, and then this whole fraction will become 0. Okay, and what it means that the temperature of the vessel, the batch fluid, will attain the temperature of the heating fluid if you give it infinite time, and these two temperatures become equal with an exponential decay. Okay, so that is minus t over tau. And this expression works for if you are heating your fluid or if you are cooling your fluid. So in both cases, the analysis will remain the same. The only thing that will change is that in the case of cooling, Tf will be lower than T node. Okay, it means that it will be lower than the starting point of the fluid. So again, we can rearrange the equation in more explicit form. So we have now temperature that is a function of time that is equal to Tf, that is the fluid heating fluid temperature minus the temperature difference between the heating fluid and the initial temperature times the exponential of time over tau, that is the time constant. Okay, so what this equation shows you that if you for example you have the fixed conditions, like you know what is the heating fluid, what is the temperature of the heating fluid, what is the temperature of the initial temperature of the fluid, and what is the time constant. So your final temperature will depend on the time. Okay, so if you know what temperature you have achieved, or what how quickly you can achieve a certain temperature, is based on these three variables. So that is Tf, T node, and tau. And by fixing your system in terms of the fluid or your heating geometry, you can actually make these variables as constant. Okay, so we can draw this, we can represent this equation graphically as well. So if you look at this system here, so here on y-axis you have the temperature as a function of time, and on x-axis you have the time itself. And we start with the temperature T node, that is the initial temperature of the fluid, and we have an exponential increase in the temperature. And finally, if so here, for example, in 10 minutes, let's say, in 10 minutes we reach to this temperature, while if we want our fluid, the vessel fluid, to reach the temperature of the heating fluid, we might need to give it infinite time, because as we are moving up in time, the driving force is becoming less and less. Okay, so at this point we have quite a huge driving force, that is Tf minus T, but as we are moving along the time, the driving force is becoming less and less, and that's why it takes infinite time or mathematically it takes infinite time for the vessel fluid to become to the temperature of the heating fluid. But in reality, actually, it will never happen because there are always losses. So we don't have to give infinite time. We give it practical time, for example, 20 minutes, 30 minutes, 2 hours, whatever, where the delta is an acceptable range. Okay. So we can apply this analysis also for cooling and graphically just to show you how it will work. So for the cooling, we can say that the T node will be actually lower than TF. Okay, so that will be when we are doing cooling. Okay, we have a refrigerant now in the jacket, and if you do that, you will have a similar curve that, as you can see, it's just down, and it means that now you will have a decrease in temperature with an exponential decay. Okay, so that is exactly the same as I said in the previous slide. So this analysis, as I said, is used for steam as a heating fluid. It means that the temperature of the steam is not changing, okay, because steam has a constant temperature. So you have steam, it's being condensed and leave. So even if the steam is being condensed, the temperature of the steam does not change. It just changes its phase. And by change of this phase, it provides the latent heat for the heating of this vessel fluid, okay? But there are other ways we can heat this fluid. So for example, we can use direct steam injection. It means that we are feeding steam to the reactor. But because we are feeding steam to the reactor, so when it is heating the fluid, it's also increasing its volume because steam is being condensed when it is heating the system. Okay. The second method can be that we are using direct electric heating. So it means that we are using heater, for example, heater wires to heat this system. And if we are doing that, it means that the heating rate is constant because that's the heat provided by electrical heater, and we have linear increase of temperature in time because it's happening through conduction. And finally, we have the last option where we can use a heating fluid. So instead of using steam that is at a constant temperature, we are actually using a heating or a cooling fluid in the jacket. Okay. But in this case now, because the system that is in the jacket is providing its heat to the system that is in the batch or in the vessel, it's also becoming cold in time. Okay, and that is what we call heat exchanger. And we will look at this last case in much more detail in the next lecture, where the heat is happening between a hot and a cold fluid through a jacket or through an exchanger. Okay. So that is all for this part. Thank you for your time.